So you want to learn about linear inequalities? Oh, don't you worry, you know I've got you covered. This will be a fun, smooth, easygoing, streamlined ride. Numerically, linear inequalities look something like this. Definition-wise, a linear inequality is a statement that compares two expressions using inequality symbols. Basically, they're normal linear equations, just with a sense of direction. What do I mean by that? Well, let's break down what an inequality is. Sorry, overused online joke. I really need to go touch grass. There are four symbols that are used to describe inequalities. Less than, greater than, less than or equal to, and greater than or equal to. I like to remember the or equal to symbols by the line underneath. Notice how it looks like an equal sign cut in half and replaced with the directional sign on top. This is easier to visualize on a number line. Let's take x equals 5. All numbers less than x equals 5 would be this region, with an open circle at x equals 5 because 5 is not included.
So what about or equal sign, asks you?
If you're asked for all numbers less than or equal to x equals 5, the region shaded on the number line would still be all numbers before 5, with a closed circle at x equals 5, because x equals 5 is included in the solution set. Easy? Good. Here comes the fun part. See this linear equation? Get rid of the equal sign, replace it with any inequality symbol. Let's do greater than or equal to. And well, bam! Linear equation out, linear equality in. But what does this really mean? Well, let's take it by face value. This inequality reads y is greater than or equal to 2x plus 6. Or, even better, the output is greater than or equal to 2 times the input plus 6. In other words, we're looking for all points where y is at least as big as the line y equals 2x plus 6. Let's see how this would look on a graph. First, we graph the linear equation y equals 2x plus 6. Then, remembering that we're trying to find all y values greater than y equals 2x plus 6, this gives us a big fat shaded region above the linear equation. But remember, we're also looking for values that are equal to y equals 2x plus 6, so we include the equation y equals 2x plus 6 by using a solid line for the graph. I specifically emphasize solid line, because if we were to do this linear equality changing greater than or equal to strictly greater than, then we would have to use a dotted line, because the line y equals 2x plus 6 is not included in the solution set. The same ideas apply to their not-so-distant cousins, less than and less than or equal to. Except for these two inequalities, the region shaded will be underneath the line graphed. But why is this the case? Well, let's use the same graph and choose any random coordinate in the shaded region. Let's say 5, 20. When we plug in 5 into the regional equation, we get y equals 16. Now, using the handy-dandy Samani linear inequality, we see that y equals 20 from our chosen coordinate is bigger than the output y equals 16 we got from our equation, which makes sense in the larger picture of our inequality.
Yay!
Fun, right? Well, good, because we're about to play double and give it to the next person. Compound inequalities can mean 2, 3, 5, or 10 billion different inequalities. Before you have a stroke, you'll most likely only be dealing with 2 and at most 3 linear inequalities in algebra. Here, these two symbols will come in handy. The right side U symbol means or, and the upside down U symbol means and. An easy way I like to remember the and symbol is to notice how the upside down U looks like an A with a line in the middle. A for and. Compound inequalities look something like this, where the two functions are related with an or an and. Let's first look at or. Say we have these two inequalities. Since the coordinate can be less than or equal to the first or the second, our solution set includes any coordinate that is less than or equal to either of these functions. When we graph each of these functions on the same graph, we get something like this. Following the inequality symbol of less than or equal to for both functions, we get this shaded region for the red function and this region for the blue function. And because it's or, we don't have to pick. We can just smush the shaded regions together and boom, that's our whole solution set. Everything in either shaded region. Now, let's do and. And is like the spoiled younger brother, in that it's very picky. In order to be in the final solution set, the coordinate has to be in both solution sets, less than or equal to the blue function, and less than or equal to the red function. With and, we only keep the area where the red and blue overlap. It's like a tight, wholesome hug. But wait, there's more. Moving away from the coordinate system, you may also be asked to solve an inequality with only the equation. Take this inequality, for example. This question is asking you to find all x values that when plugged into this equation is greater than 11. The rule of thumb that you by all circumstances must remember is this. You can do anything to both sides, add, subtract, multiply, or divide, as long as you do it equally to both sides. Why? Because inequalities are about comparing sizes. If you mess with one side more than the other, there's really no point in comparing the two. But wait! There's even more! If you multiply or divide both sides by a negative number, you also have to remember to reverse the inequality sign. Think about it like this. When you multiply or divide by a negative number on both sides, you're flipping the sign on both sides as well, which you can also think about as flipping the number line. In a positive normal realm, the right side gets larger and the left side gets smaller. But when we flip the negative realm, the right side gets smaller and the left side gets larger. For example, 2 is greater than negative 1. Now, multiply both sides by negative 2, the number line has now flipped. Even though normally 4 is greater than 2, because 4 is negative, negative 4 is less than negative 2, which means the inequality has also flipped. Back to our original example, we can use the rules we just learned to solve for the solution set. We first add 9 to both sides to isolate x, and then divide by a negative 4 on both sides. And yay, we're done! Right? Wrong. Because we divided by a negative, we have to also flip the inequality, so the correct answer would be x is less than negative 5, which on a number line would look like this.